Okay. Yes. Hello, everybody. Today, I'm basically continuing on from Kasra's talk last week. Yeah. So to recap what we saw last time, so we were looking at entanglement, and we were looking at how cohomology can be used to measure entanglement. So we begin with a state. So that's just an element of some Hilbert space, and the n-partite Hilbert. Okay, I can still hear the echo. I can't lie. Okay, I'm just gonna stop. Okay. Okay, so we begin with a state which is an element of an n-partite Hilbert space, and we say that a state is entangled if you can't break this up into a product of n different if it's not a product space, which means you can break it up into a product of this form, where each of these is in, h1 up until hn. So if we can't break up a state into this form, then it's entangled, basically. And we wanted to see how we can use cohomology to measure this. So in order to, and also as a side note, we can expand such a state in this form. Also, okay, I should probably mention that this ket notation, it basically denotes a vector. So it's just an element of this Hilbert space. And then you might see a bra, which is just the dual. So like if we're dealing with like a one by n, vector, then the dual will be like a n by one row, like for example. So that's what the bras and the kets mean. Anyway, so with a state like this, we saw that we could form something called a pure state density matrix, which is this product here. And if we can write it, in general, we can write a density matrix in the following form, and where these lambda a's, they act like probabilities. So if you sum all of these lambdas, they give you 1. And we define the support projection by just basically dropping these coefficients. And the importance of the support projection was, when it came, so we want to define cohomology because we're using cohomology to measure the entanglement. And we sort of used de Rham cohomology type language, basically, to describe everything. So we described a K-form as a K-form on an n-partite space. So this is like if you think about de Rham cohomology, this is like a K-form on like a n manifold, basically. So it's a tuple with n choose k terms, and it's linear operates. So for example, I don't know, if we're looking at a 2 form on a HABC, 3 choose 2 is 3, so it'll be a 3 thruple, if you will. And what will it be? Well, since it's a 2 form, we choose all the different combinations of linear operators that act on, so like AB, then we'll have AC and BC. And we also want to restrict them to the image of this pure state density matrix. And the way we do that is by acting on the left and the right by the support projections. So it'll be like SAB here and then SAC and so on and so forth. Blah, blah. And we saw last time how to form a bipartite complex. So we began considering what this cohomology would do. And we saw that these differentials were given by, so if we're given some lambda, D0 will give you this pair lambda SA lambda SB. And then D1 will take you, so if you're given, some operators OA, OB, where they're restricted, so they're restricted to row A, restricted to row B, then this D1 will send you to, I believe it's OA times the identity on B minus the identity on A times OB, and then you restrict that to row AB. And notice that this is a two-form because we've got one guy acting on AB, and then we restrict it to the image of row AB. So in today's talk, what we want to do is we want to first define, so we've defined bipartite cohomology, but now we want to generalize it to multipartite cohomology. Then, well, we're gonna do that, and then what we're gonna see is that our cohomologies actually turn out to enjoy symmetry, and the way that we're going to explain this is first we need to so we're going to do basically Hodge theory, but on our instead of doing it, on manifolds and stuff, we're going to do it on pure, we're going to do it on density matrices and n-partite states and stuff, and I'll try and explain how we do that basically. And the goal is to show that this symmetry that we observe is actually true. So before we start observing any symmetry, we need to define what multipartite cohomology is. So before we look at the case of multipartite cohomology, it would be helpful to look at tripartite cohomology to really get a sense of where the definitions are coming from. So just like last time, we define D0 and D1 very similarly to the bipartite complex. So this time, instead of sending lambda to lambda SA, lambda SB, we just send lambda to lambda SA, lambda SB, lambda SC. So three pair, because this is a one form on a three-partite space instead of a two-partite space. And D1, so this now we're sending everything here is suitably restricted. I just didn't have enough space to write it on a equation, but everything here is restricted to row A, row B, and so on. And we send these three linear operators to, well, this is exactly what D1 did before on the bipartite state, but this time because we're working with three different subsystems, we need to do this for AB, but also for AC and for BC. So we do that basically. We act exactly as D1 would, but just two more times. So, okay, that seems very natural. But now, of course, the question is, well, we have no idea what D2 will be. So all we know about D2 is that it's going to send a two form on this three-partite space to a three form. So how can we do that? Well, the first guess could be, why not do in a similar fashion to before? So we take this our operator acting on BC, and we just times it by the identity on A. We take our operator acting on AC and just times it by the identity on B. And we take the operator on AB and we times it by the identity on C. And here we should end up with something acting on ABC, and then we just restrict it to row ABC, and there we go, we're done. However, there's a couple of problems here. First one is, if you look closely at this middle term, this isn't actually acting on HA, HB, HC, it's actually acting on HA, HC, HB. So it's acting in the wrong order, basically. And also another slightly more minor issue, but still, an issue, which sort of we'd like to address, is that it doesn't satisfy the Leibniz rule. Now, obviously, right now, because we don't have a notion of the wedge product, that doesn't mean anything, basically. But later on, when we define the wedge product, we would be able to show that this doesn't actually satisfy the Leibniz rule. But thankfully, there is an easy fix for that, so which I'll explain in the next slide. Or in 2 slides. But okay, first we need to solve this first issue, because this first issue is pretty bad. So what we do is we define a slightly different version of the tensor product. So because we're acting on, HACB, essentially, this is very similar to, if we're thinking about this in terms of de Rham, instead of acting on dx, dy, dz, it's sort of like acting on dx, dz, dy. And the way that you solve this in, normal de Rham cohomology is you just stick a minus sign in front of it, basically. And so we'll do something similar, and we'll define this new tensor product which shifts things appropriately, basically. So if we're given 2 different operators, A and B, which act on I1 up until IA and J1 up until JB, then, okay, firstly, we'll define a new set of indices, which basically just combines all of these indices together and just puts them in order. So, for example, if this is acting on A is acting on A, C, E, and B is acting on B, B, D, or something like that, then our new set of indices K would be A, B, C, D, E. So, in order, basically. And the permutation that takes you from A, C, E, B, D to A, B, C, D, E, we'll call that sigma. And we'll define a new operator C, which is just given by A, K, if K is one of these indices, and BK if B is one of these J indices. And then what we simply do is we define the I don't even know what to call this shuffled, I'll call it the shuffled tensor product of A and B to be this tensor product of our new operator, which is just these 2 glued together, except now we take into account the permutation sigma. So we stick a -1 to the sigma in front of it. And this tensor product will allow us to shuffle the different operators appropriately. So instead of, for example, with this definition, OA times OC times OB to go from ACB to ABC, that's an odd permutation. So now we have to stick a minus sign in front to swap these 2 around. Now what we have is that the differential is now this operator acting on BC times the identity on A, plus this operator on AC times the identity on B, plus this operator on AB times the identity on C, all restricted to ABC, except now we're using the shuffled tensor product. And this shuffled tensor product actually doesn't do anything to these 2 guys because they're acting in the correct order anyway. And this 2 here is dealing with the Leibniz product, the Leibniz rule. because when you prove the Leibniz rule for de Rham cohomology, you use the product rule. But obviously, because we're not working with functions and derivatives, there is no such thing as the product rule. Now, the product rule generates two terms. So, in this case, we'll just multiply by 2, and, that turns out to work. So that's what this factor of 2 is doing. And that's why we have these shuffled tensor products. So, now, with this new, with these new tools in hand, we can now define cohomology in general for any n-partite space. So, if we're given some state on an n-partite Hilbert space and its associated density matrix, then we can define this multipartite chain complex where, again, D0 is acting exactly the same way as before, except n times. And now dm is this weird thing where we have a Cartesian product with over all of the, so dm sends us to a Cartesian product over all of the subsystems of length m plus 1 of this thing. So remember before how we had OBC times by IA. So we take, this is for D2, so we now operating over systems of length 3. So the only length 3 thing we have is ABC. So the first thing we could do is take out A and replace it by the identity. Then we can take out B and replace that by the identity. And then we can take out C and replace that by the identity. And with the appropriate shuffling as well. And that's exactly what this sum here is representing. So,
Greg, is there a factor of m missing inside the sum? Because for Leibniz,
yeah,
right?
Yes, there is a factor of m missing. Yeah, that is true. So these terms here are just representing that. So we take our system of length m plus 1, we remove one of the elements and replace it by the identity, and then we add all of those different possibilities together. And we take and we do that for every single possible m plus 1 length I don't even know what the word is. M plus 1 length
like a tuple
system we can, tuple we can come up with. So for example, how this worked for D1 is so if we go back up to D1, D1. So for D1, it takes us to all of the different possible tuples. So first we have AB, then we have AC, and then we have BC. Now with AB, first thing we can do is take away the A and replace that by the identity. And the second thing we can do is take away the B and replace that with the identity. And then we just do that for all the different possible combinations, and we put them all together into a tuple, into a Cartesian product. And as Furco points out, there is also a factor of m that we times by in order to mimic the Leibniz, in order to satisfy the Leibniz rule and mimic the product rule. And that is our definition of the multipartite complex. So I guess I'll ask if there's any questions. Also, if there's any in the chat, then let me know, because I'm recording my screen, so I don't want to switch to Discord.
Yeah, I see nothing in the chat now.
Okay. All right then. Well, if anybody has any questions while I'm talking as well, then don't hesitate to interrupt me. But okay. Now, okay. So now that we know what multipartite cohomology is, we can start to look for patterns. And one pattern that Furco and I saw when we were first reading the paper is this symmetry that it ended up actually working. And that must have been like 2 years ago now. But basically, if you package all of the dimensions of the cohomologies together into a Poincare polynomial, which it's just a polynomial where the coefficients are all the dimensions of the cohomologies, basically. And it's just a way of collecting together all the information into one thing, basically. So if you look at these Poincare polynomials for the GHZ state, which I think Kasra talks about in his 2-qubit example. Anyway, if you look at the Poincare polynomials for this, for the 2-partite case, it's just 6, because there's only one cohomology and its dimension is 6. Then for the 3-partite case, we have that the H1, so the cohomology, the first cohomology, the dimension of that is 7. And the dimension of H2 is also 7. Then for the 4-partite case, we have that H1 is 9, H2 is 12, and H3 is also 9, and so on and so forth. So we have H1 is 11 for the 5-partite case, H2 is 20, H3 is 20. But basically what you can see is that these polynomials are all symmetric. And so now you start to think, well, is that a coincidence? And as we'll see maybe in Ishan's talk, we checked lots of these polynomials in code, and for any state that we would input, the Poincare polynomials would always be symmetric. So the approach that we take is very, very similar to that of Hodge theory. So the approach in Hodge theory is we define a map called the Hodge Star, which takes a K form and outputs an n minus K form. Then you use this to define an inner product, and you use the inner product to define a co-differential delta, which instead of taking you up from K forms to K plus 1 forms, takes you down from K forms to K minus 1 forms. And you define the space of harmonic forms, where a harmonic form is something that's eliminated by both delta and our original differential D. And you show that these harmonic forms are actually, the space of these harmonic forms is isomorphic to the cohomology. And you use the Hodge star to show that these harmonic forms are actually, the space of harmonic K forms is isomorphic to the space of harmonic n minus K forms. That's where the Hodge star comes in. And then, well, given these two isomorphisms, we can then put them together to say, well, HK is isomorphic to the harmonic forms, and that's isomorphic to the n minus K harmonic forms. But then we use this isomorphism to show that this is isomorphic to the n minus K cohomology. And in that way, you can show why there's a symmetry happening. So we'll just do this step by step. So we have to define a Hodge star. Then we have to come up with what this co-differential is. Okay, then the definition of harmonic forms becomes quite clear. But then we also have to show that these harmonic forms are telling us everything about the cohomology groups. And then finally, we have to take this definition we started with and apply it to show that the space of harmonic k-forms is isomorphic to the space of harmonic n-minus k-forms. And then everything is easy. It's just exactly what I've written here. So that seems like a lot of work, so we might as well just crack on. No time like the present. So we start with the Hodge star. So if we're given a state, what we can do with the state is we can decompose it into an easier form. So we can decompose it into the following sum, and this is known as a Schmidt decomposition. And with this Schmidt decomposition, the support projections, which we defined in the earlier talk and in the recap, are just given by this sum here. So we drop our coefficients, the support projections on some index of length, I don't know, k, are given by this sum here.
Greg, just to comment,
so,
I mean, it was not at all obvious that this was going to work a priori, because a Schmidt decomposition only works on a bipartite system, right? So part of the reason why we thought this was going to fail initially is because how could you possibly do a Schmidt decomposition on a 3 or 4 or 5-partite system? But the point is, in the circled equation there, the I and the I complement, right? So for any system with like n subsystems, you can always coarse grain and pick k of them, and think of the big n-partite system as a bipartite system where A is k of them and B is the other n minus k. So you can always split it. And that's the only reason this works, right?
Okay, yeah. Okay, yeah. Okay, that makes sense, yeah. So, okay, yeah. So you think of it as a bipartite system. Okay, so a Schmidt decomposition. Okay, yeah. Schmidt decomposition is a way of decomposing a bipartite system into the following form. But obviously, because we're dealing with n-partite states, okay, well, how is that going to work? Well, we just define A as this length k subsystem, and then B is just the rest of them. So I complement. Also, this should be up here, but yeah, as I complement, and then we can decompose it in the following form. And then the support projections will end up being this sum here. And so, because we are a k-form is acted on by the support projections on the left and the right. So remember that a k-form is just something of the form Si times by O times by Si. So it's acted on on the left and the right. So it's a linear operator on a vector space which has basis vectors I alpha. Remember, this ket notation is denoting elements of a vector space, so just vectors basically. And so if it's a linear operator on a space with basis vectors I alpha, then we can write it in this form, where these omega alpha betas are the coefficients of some matrix of this form. And so what we do with these coefficients is we take the complex conjugate, and because we want to go from k forms to n minus k forms, we now, instead of acting on this length k subsystem I, we take the complement, which will then take us down to a length n minus k subsystem, and we do the same procedure, and then also we insert a little we insert this minus sign to account for the shuffling. So this I union I complement isn't in order yet, so we take into account the fact that we have to reshuffle from I union the complement to our original order, our original indexing. And there was actually a reason for why we take the complex conjugate. I think it's because if you don't take the complex conjugate, this won't be well defined, because with these basis vectors you can rotate them a bit or something like that.
Yeah, we can see it if you go back one slide more easily to the Schmidt decomposition, because in this one, yeah, good. So it's clear that the Schmidt decomposition is not unique, because on the right side of that first equation, if I chose to multiply all of the alpha i's by some complex phases, like e to the I theta sub alpha, so I multiply all of those by some complex numbers, and I multiply all the second guys by the opposite angles, e to the minus I theta alpha, then those two cancel out and the expression is the same. So the Schmidt decomposition is not unique. You can always rotate phases. So in order to make this thing invariant under changing the phases, what we do is put in the complex conjugation, because what that does is it compensates for those phases if you do a rotation. If you rotate those two guys by angles and then pick one of the two, right? We pick like the I and then flip to the I complement. So if you pick the I, you get the e to the I theta alpha, and then you complex conjugate it so it goes to e to the minus I theta alpha. And then that matches what would be on the alpha I complement, because remember, we're trading I for I complement. So you need to get the phases to match, basically.
Yeah. So that's why we take the complex conjugate, so that it's all well defined. And, well, we can also see that if we do the Hodge Star twice, well, these guys are going to return to those guys. The complex conjugate of the complex conjugate, well, that's just going to return us back to here. So what we're going to get is, well, we shuffled it, sort of, if we shuffle it k times the first time round, then to shuffle it back in order, we have to shuffle it n minus k times. So in total, all that doing the Hodge Star twice does is, well, it sends us from a k form to an n minus k form, and then back to a k form, and it's not quite the identity, but it's the identity up to a sign, and that sign is -1 to the k times by n minus k. So that will be important later, that the Hodge Star twice is almost the identity up to a sign. So that's what the Hodge Star does. So this is how we define a map which takes us from a k form into an n minus k form. And yeah, so and it's well defined, it works nicely. And when you do the Hodge Star twice, it gives us plus or minus the identity up to a sign. Okay, so now the next thing we need is the wedge product. And the reason we need the wedge product is what we want to do is define an inner product. So, and the reason we want to define an inner product is because we want to attach an inner product space structure onto the space of k forms. And the reason we want to do that is using that inner product space structure, then we can use that to define our co-differential delta. So in order to define the inner product, we're going to use a wedge product, a notion of the wedge product, because that's how it's done normally in Hodge theory, I think. So the wedge product of two entanglement forms is we take two forms, and say this omega is a K form and this eta is a M form. Well, then we can see from this sum that it's going to take us to a K plus M form, assuming that none of these indices are the same. Otherwise, it'll just give us 0. Because the shuffled product will give us 0 if we have, so for example, if we have OA shuffled times OA, that takes us to 0. So if we're given two entanglement forms, omega and eta, which don't overlap at all, with these subsystems, then we get a K plus M form. And an example of how this works is if we take two 1 forms on a bipartite space, then what we're going to get is, 1 plus 1 is 2, so we're going to get a 2 form. And, okay, so we just have to apply this sum. So first thing we do is omega A times eta A. Then we add omega A times eta B. Then we do omega B times eta A and omega B times eta B. And we restrict it to the union of these two, which is just AB. Now, this thing here is just 0. This thing here is just 0. And, according to our notion of the shuffled wedge product, this thing here is just going to be minus eta A times omega B. So overall, we're left with this as the wedge product. So that's just an example of how it works. So it takes an N form it takes a K form and an M form and sends us to a K plus M form in the following way. In a very natural sort of definition, I think. So now that we have this, we can define the inner product. Now, if we're of two different K forms, so given two entanglement K forms, omega and eta, their inner product is given by the trace of, what are we taking the trace of? So we do the wedge product of omega and the Hodge Star of eta. Why? And we restrict it to row 1 up until n. So how does this exactly work? Well, we're given a K form, omega. So this is a K form. And when we take the Hodge Star of eta, that gives us an n minus K form. And when we take their wedge product, if we add these two together, it's going to give us an n form. So that's why we need to restrict it to this row. And we want a number because we want the inner product to give us a number. So we take the trace of this matrix that we end up with. And in the paper there are a bunch of summations and stuff like that, which give this definition in a more sort of explicit form. And through that form, you can also show that this gives us an inner product space structure. Now, I'm not going to go through those calculations because for me, I think the most important part is that we've successfully defined an inner product, and that is what allows us to continue. But obviously, if you want to get into the nitty gritty, then all of the calculations are in the paper. And you're free to
just say the properties though, that it's positive semi-definite, that it's linear in the first argument and anti-linear in the second argument. That's basically all you need, right, for the inner product.
Yeah. So it's linear in the first argument. So like equals a like x z plus b y z, and oh god, I'm blanking. What's the third
problem? If you flip the order, you get a complex.
Oh, it's the yeah.
Which is weird if you're used to real vector spaces, but that's a standard thing in a complex vector space, that if you flip the order, you should complex conjugate them.
Yeah, exactly. And also another important property that I'll mention now is that this is equal to 0 if and only if x is 0 as well. Because I think that gets used in a proof later on. So these are the properties of an inner product space, and these are the properties that this inner product enjoys. And yeah, that's what's important. That's what we wanted basically. And now we can really, get moving with our proof of this symmetry. So the first order of business is defining what this delta is. So because we now have a finite dimensional inner product space structure on our K-forms, we can define an adjoint operator, delta, to our differential D, which satisfies the property that if we're given the inner product of omega and d eta, this is the same thing as doing delta on omega and then inner producting that with eta. And for those of you who studied category theory, this looks exactly the same as the definition of a joint functor. Actually, maybe Dennis has some words on that, but we'll ignore that for now. But this is the existence of delta is guaranteed because we have defined a finite dimensional inner product structure on omega k. And notice that when we have delta delta, we get 0. And this is because, well, remember that the defining property of a chain or a cochain complex is that the differential, when you apply it twice, it gives you 0. Twice in a row, it gives you 0. So if we have omega d d eta, that's just delta delta omega eta. But, well, if you think about it, omega 0, the inner product of anything in 0 is 0. And therefore, well, since I'm assuming eta is non-zero, that means that delta delta omega must also be 0. And so, since these were arbitrary forms, that means that delta delta applied to anything is giving us 0. And furthermore, it can also be shown that delta is the same thing. So delta omega is the same thing as doing the Hodge Star of omega, then applying the differential d, then taking the Hodge Star of that, and then we also have to multiply it by some constant Cnk, which again is explicitly calculated in the paper, but is not important for this talk. It's just some constant. And also we also have some sign, either plus or minus 1. So if we think about it, so if we start with a K form, the Hodge Star, oh dear. The Hodge Star takes us to an n minus k form. Then we act with the differential, which takes us to an n minus k plus 1 form. Then we do the Hodge Star again, which takes us to an n minus k plus 1, which is a k minus 1 form, and then we times it by some numbers. So the delta is taking us from the k forms to the k minus 1 forms. So that's how it's acting. And again, this relation here is going to be very important in the future. So before we proceed, we have to get a lemma out of the way, which is pretty important for the proof. So if we have a cochain complex where each of these v's are finite dimensional Hilbert spaces, which again for us is definitely true because we're working with n-partite spaces, so those are finite dimensional Hilbert spaces. And where each of these have an inner product structure, well, we've defined an inner product structure on omega k. Then, if we're given a co-differential, which takes us from k forms to k minus 1 forms, which we have, which is adjoint to this differential, then in each cohomology class, there is a unique element which is annihilated by delta, and which is and it also has the property that it's the representative with the smallest norm and the norm is, by the way, just omega with the smallest norm in its cohomology class. So okay, let's I don't think I proved this actually. So what does this mean? This means that for every cohomology class, omega, there is some element in here which let's call it I don't know, eta, where delta eta is 0. And this also happens to be the form which has the smallest value of eta, the inner product with itself. Okay, now let's see how we can use this to our advantage. Oh no, that is a spoiler alert. Okay, there we go. Okay, so first of all, we define what a harmonic form is. So a harmonic form is a form where d eta is 0 and delta eta is 0. Okay. Now, if eta is in some cohomology class omega, then it's the harmonic representative of that cohomology class. And the proposition above has shown that, well, okay, we know that every cohomology class has an element such that delta eta equals 0. So every cohomology class has a harmonic representative. Why harmonic? Well, remember that the cohomology is just the kernel of D mod the image of D. So every element in this cohomology class will be eliminated by D. So we've guaranteed that it has a harmonic representative. But what we need to show is that we can't have two harmonic representatives for a cohomology class, because otherwise we'd have too many harmonic forms. So we want we want there to be an isomorphism between these two spaces, because that was part of our action plan before. So
it is interesting that does happen in infinite dimensions. So it's often the case that, for instance, de Rham cohomology on an infinite dimensional manifold does not have a Hodge isomorphism and has a Hodge homomorphism, precisely because of this. You don't get it to go both ways. So it's non-trivial to show this, basically.
Yes. So we've shown that we have a surjection. by the, well, we haven't shown it, but okay. We have this important lemma, this maths lemma, which tells us that it's a surjection. And so now we need to show that it's an injection. So, okay, well, we'll just use the definition of, we don't need to do anything fancy. We'll just use the definition of an injection and see where that takes us. So let's say that f of, oh, also I should define what f is. F sends omega, this harmonic form omega, to its cohomology class. Now, let's say that omega has the same cohomology class as eta, where these are both harmonic forms. Now, what we want to show is that this implies that omega equals eta. So, if two things are in the same cohomology class, well, okay, and let's not be fooled by the fancy word cohomology. This is just a quotient group. So, what this really means is that their difference, well, remember, we're doing the kernel mod the image. So what being in the same cohomology class really means is that their difference is in the image of dk minus 1. That's just quotient groups. So for example, if we're in, like, I don't know, the integers mod 5, then two things are the same mod 5 if, their difference is divisible by 5. And, it's the same reason why this is happening. So we have this. This is by assumption. Now, what we're going to do is we're going to take the inner product of omega minus eta with itself. Now, because of this property, we can just sub that in. And now remember, d and delta are a joint. So this is the same thing as lambda, the inner product of lambda and delta of omega minus eta. But these are harmonic forms, and so this is 0. And so the whole thing is 0, and well, that means that the inner product of omega minus eta with itself is 0, but that is only true if omega minus eta is equal to 0, which means that omega is equal to eta, as we required. And so we have a bijection, and it's also linear and stuff. So it's an isomorphism. So that is very good. That is very good indeed. What we have now is we've defined harmonic forms, and we've shown that this is the isomorphic to the kth cohomology group. So that's very good. Now the last step is we need to show that this is also isomorphic to n minus k harmonic forms. And this is where, like a phoenix rising from the ashes, the Hodge Star, the Hodge Star comes back to save the day. So what we need to show is that the Hodge Star takes a harmonic k form and it gives us a harmonic n minus k form. So note that we know that it takes a k form to an n minus k form, but we don't know that it takes, we don't necessarily know that it will take a harmonic k form to an harmonic n minus k form. So that's non-trivial, so we need to show that. So let's assume that omega is a harmonic k form. Then, what do we want to show? What we want is for the Hodge star of omega to be eliminated by both d and delta, because then that would imply that it's also a harmonic form. So we're just going to literally do this by computation. So d applied to the Hodge star of omega is, well, remember that star is just the same as minus 1 to the k n minus k. So if we times both sides by minus 1 to the k n minus k, then we have that minus 1 to the k n minus k times by star star is the same as just doing nothing. So we can insert a star star minus 1 sphere k n minus k over here. And it's the same thing. However, this part here, I'm going to use a different color now. This blue thing here, well, remember that delta was proportional to star d star up to a sign and these coefficients c and k. That's what these c and k are doing here. They're the coefficients that we defined a few slides ago. Oh no, we didn't define, but I stated that they exist basically. And they're defined explicitly in the paper. But essentially, the coefficients themselves don't matter. Essentially, what we have is that this part here becomes delta omega. And, well, okay, we're still left with some sign divided by some coefficient. And then we also have to take the Hodge star. But because we've assumed that omega is harmonic, this thing here is 0. And so, well, it doesn't really matter what this stuff does because it's just going to give us 0 again. And so Hodge star of omega is also eliminated by D. That's good. And we're going to use a very similar reasoning to show that delta is eliminated by, Hodge star is eliminated by delta. So, delta is, again, as I say, it's plus or minus some coefficient c n k times by star d star. So, okay, let's plug that in. We get this. Star star just gives us another minus sign, so we'll just absorb that into this plus minus. And then we're left with something d omega, and d omega is 0 by assumption. And so star, and so the whole thing is 0. And so star omega is eliminated by d, and it's eliminated by delta, so it's a harmonic n minus k form. And similarly, of course, we can do the exact same reasoning to go the other way, so from an n minus k form to a k form. And so because the Hodge star applied to itself is plus or minus the identity, it's going to be an isomorphism because, well, it's its own inverse, you know. All we need to do is plug in a sign and we have the inverse. And so, well, any function which has an inverse, if we can define f from a to b and f inverse from b to a, then that's going to be a bijection between b and a. And so so the Hodge star provides us with an isomorphism between harmonic k forms and harmonic n minus k forms. And, well, now we're done. We've done everything that we wanted to do. And so now all we need to do is combine this into a sentence. And we've proven our duality, which we wanted to prove. And that is the following. The dimension of the kth cohomology of some n-partite of some density matrix on an n-partite space is the same as the n minus kth the dimension of the n minus kth cohomology. And all we need to do is just combine everything. So we showed via the important lemma and using the inner product structure that the kth cohomology is the same thing as the harmonic k forms. Then we use the Hodge star to show that the harmonic k forms are isomorphic to the harmonic n minus k forms. And then again, we just use this same isomorphism to go from here to here. And so we have an isomorphism between the kth cohomology and the n minus kth cohomology. And that is the main result that is proven in the paper. And yeah, hopefully I explained it somewhat well. There is also the Hodge decomposition, which I didn't decide to go into, and the Laplacian operator, because I don't think I really needed it for the talk. But that also, a notion of that also exists, and is nicely defined as well. But yeah, that's basically how we showed that these Poincare polynomials are symmetric. So yeah, I guess now is the time for questions and interesting discussion. Yeah.
Maybe first a round of applause, virtually or otherwise, for Greg. It was a beautiful talk, actually. I mean, it's I think it's clear you understand all of the ingredients very well, which is good.
Thank you. Thank you. Okay.
Questions from anyone? I guess I can ask, was it surprising to you that this actually worked? Because for a long time I thought the Hodge Star was not going to work at all. Like, does this seem obvious to you now, or is it still surprising? Are you jaded or something?
That's a good question. I mean, I think that, yeah. I mean, okay. Once the Hodge Star worked, then it's like, then okay, it's not very surprising anymore. But yeah, there was quite a long period of time where sort of we just had to say, oh, this Hodge Star, doesn't work, so we're gonna have to do something else. But it is surprising. But it's nice. I mean, the only reason it's not that surprising is because there was so much like computational evidence that it sort of had to be true. But I'm sort of glad that I mean, it is nice that it works so similarly to just de Rham, instead of having to do some completely new like way of proving this. But yeah.
Yeah, I thought we would have to do some gymnastics and only use an inner product but no Hodge, because like, I mean, you probably remember, but the reason why I thought this could never work is, suppose you have a bipartite Hilbert space where HA is a qubit, so it's two-dimensional, and HB is like 1,000-dit, so it's 1,000-dimensional Hilbert space. It's huge. How could it
Yeah.
possibly be that there's something that star star is the identity? Because if you're compressing down, you're crunching down from 1,000-dimensional Hilbert space to a two-dimensional Hilbert space, and then doing star again to go from two back into the 1,000-dimensional thing. How could that possibly be the identity? Because the
Yeah.
dimensions are so different. But I mean, the magic, I think it basically, that when I was talking to Kasra about how to prove the support projection stuff in a dumb way with indices, and then I was playing around with, oh, why don't we just prove this with the Schmidt decomposition? And I'm like, oh,
Yeah.
wait, but the Schmidt decomposition does everything. That solves all of our problems, because it's not
Yeah.
really a two-dimensional Hilbert space into a 1,000-dimensional Hilbert space. It's really 2 and 2 because it's fixed by the Schmidt rank. So this is it's kind of magical, because it only works because of Schmidt, and this would have failed if the parent state was a mixed state instead of a pure state. This only works for pure states upstairs, right, in the parent Hilbert space. So somehow the pure states are very special. But I don't know. I think it's a very cute, beautiful result. Even though the math is very simple, like none of the proofs require any fancy technology, basically.
Yeah.
It's still kind of surprising, and it has like a sort of elegance and like a sort of inevitability to me, where you kind of see where the proofs are going and you know it has to work, but you don't quite know how it's going to work. And then when you see the
Yeah.
ingredients come together, it's like, aha, then it's satisfying.
Yeah.
Right?
Yeah. It's one of those ones. Yeah. I do find it somewhat funny that I think this lemma wasn't it like an exercise in some like notes somewhere?
That was in Jose Figueroa O'Farrell's lecture notes on BRST. And I think I asked you to do this in summer 2023 when I was in Padova, if you remember. So that was like a year and a half ago almost. So
Yeah.
this
Yeah.
was like, that was the key ingredient. Like, that was the conceptual insight we needed to know that this would work if you just had an inner product, right? Because this only
Yeah.
says inner products. It does not say Hodge anywhere.
Yeah.
So here we knew it had to work with an inner product, and then I thought, oh, you're never going to get a Hodge. You're only going to get an inner product. And then finally, talking to Arcat, we got the Hodge Star as well. So
Yeah.
I'm glad it all came together, but only because of a a long period of time with many gaps. Like if we had been working on this in a concentrated way with no breaks for like a month, I think it would have been done in a month, but I kept leaving and coming back. So I apologize that it took so long, but I hope
That's all
that
right.
in the end, I hope you're satisfied with your first paper, that it's a result that you're at least like proud of, even if it's not like the fanciest thing.
Yeah, no, I'm very happy with it. No, it's a nice one.
The fancy things shall come. I have faith in Greg. The fancy things will come.
Yeah.
Yeah, Greg can get arbitrarily fancy. I mean, now you can do the Cech-de Rham stuff, which is a little fancier, but yeah, eventually,
Yeah.
I'm sure when you go to your PhD, you'll be doing stuff that I will be unable to read or understand a word of.
That's the plan. That's the plan.
Moving up in the world.
Yeah.
Yeah, there's a lot of interesting follow-ups. I mean, one thing I was just talking to Tom about this, related to this is, so you could ask, what do the harmonic representatives actually look like? And for a bipartite, like to the simple case where you start with a bell pair, like just 1 over root 2, 0, 0 plus 1, 1 on the parent space, and then you come down and you look at the harmonic forms. The harmonic forms are all traceless. So they're traceless matrices which are in the same cohomology classes as whichever ones you started with. And Tom was very excited about this because he said, oh, if you exponentiate traceless matrices, you get SL2C matrices, right? In that case, exponential of traceless is special linear. So he was excited about this because he said, oh, there was another cohomology I was working on years ago. This is like the sixth one I've heard of now. But he said, yeah, I was working on an exponentiated cohomology where instead of looking at operators, you take matrix exponentials of those operators. And it's a little bit like going from, if you know the story of like a Lie algebra has a bunch of tangent vectors and you exponentiate Lie algebra elements to get Lie group elements by just going out along certain curves in the Lie group. So he had this like Lie group version of the cohomology where you exponentiate these things, and he thought, oh, if exponentials of the harmonic elements have natural interpretations, like they're traceless, so their exponentials are special linear elements, maybe more generally the exponentials of these things will be something interesting. So there's like a billion directions to go in for future follow-ups. I don't even know what to work on first, but I mean, for you, it seems like the Cech-de Rham is the most natural thing to do next because you basically already have it working.
Yeah, yeah. I think what would really seal the deal for me is if I managed to use the Cech-de Rham stuff, or even not even Cech-de Rham, just Maya Viatores, to prove the one of those conjectures that Tom had in his original paper. That would be good. I would be happy with that if I could do that.
Yeah, that would come back to one of the first things we wanted to do when we were reading it, right? In our list of like follow-ups.
Yeah, yeah. I mean, yeah, because it does feel like the right approach though, because especially with the Pascal's triangle, that feels like you're sort of in a way using the rank nullity theorem just on an exact sequence.
I mean, the Pascal's triangle is basically telling you that, yeah, to get each cohomology of a higher dimensional generalized GHC, you just have to sum up two other guys above and to the left and above and to the right in the lower dimensional GHCs. So if you can do that with Meyer-Vitoris, where you just take like like an open cover of the discrete set of subsystems that intersect in one guy, so like AB and BC, and then you combine those and and that tells you that, oh, to go up, you only needed to add cohomologies on AB and BC for the lower dimensional GHCs, you'd be done. I mean, that's a proof.
Yeah. But yeah, there was also because in the Pascal's triangle, there's also like you also have to add 2 at some point, like on the edges as well, or something like that. Like there's some extra like little constants that get added on like the edges or something like that.
I think the edges are easy. I think we can prove quite generally just by brute force what the 0th, or for us the first, I forget which one, I forget how we index, but the first cohomology, which for Tom is the 0th. I think we can prove those in general for GHC, because all you have to do is look at the image of the C is just lambda times the support projections, and then you just look at the kernel of D coming out of the support projections, which I think that you can prove in general. So the edges are probably fine. It's really just the bulk. The easy proof comes from the upper ones.
Yeah. But it does feel like the right way. And then, yeah, and I haven't. So I think I've proven the Maya Viatorans like works because it just works in the same way as it was just that exact sequence.
Yeah, I think I didn't go through
which
all the stuff in the notes, but it looks the same, right?
Yeah, it looks the same. I don't think I actually gave a like proper proof in general, but I did it for like 4 partite, and it just like it sort of worked immediately. It's like and it seemed very clear. I just didn't know how to write it in general, but I think it did seem very clear that like the image was equal to the kernel in that exact sequence of complexes.
I think you're right. Yeah, I mean,
and it all commuted, like because I mean it's just like restrictions or something like that. So it's like easily commutes or whatever.
Yeah, at least in the low partite systems that you were showing me, it looked like it's the same, this literal same as for like the ordinary Myra-Vitoris. So that probably works. Writing it in the general case is probably just some index fuckery where you have to be careful about like multi-index set minus j, like the way we define the general D.
Yeah.
Yeah. I think I've gotten pretty good at writing out those index fuckery. So that we can do.
Yeah.
And then if the generalized Myra-Vitoris works, then you do Cech-de Rham and prove that Cech and de Rham are the same for this thing. And then as an application, that's basically a paper. That's already without your application to the generalized GHZ. That's a paper that could be published as just the Cech-de Rham and generalized Myra-Vitoris. And then if you add an extra section at the end that says, as an application of this technology, we now prove the general results for generalized GHZ, maybe also generalized W, which are pretty easy because there's all zeros in the middle. That's an even stronger paper, right? Because then you have more results.
Yeah. That's basically what I had in mind, basically.
Oh, good. I mean, if we do it, you already have 1 paper before finishing high school, then you'll have hopefully some more before finishing undergrad, and then be in a strong position for PhDs. If you have 2 papers applying to a PhD, especially in math, it's easier to get them in physics. It's harder to get papers in math, but then I think you're in a very strong position.
Yeah, I hope so.
Yeah, if Cambridge does not email me asking for a letter, then maybe I should send unsolicited mail, drive past their house and throw a brick into the window with
Yeah, maybe don't mention my name if you're throwing bricks through windows.
Well, okay, then I just throw a brick in and then trash talk the competition, I guess, or something. Yeah, this is good. Questions from any of the others here, I guess. There were no questions in the chat, but
yes. No, I. Okay, yeah, go on. I'll let you finish typing. No. It's also okay.
pen tab,
I have this like thing. I got it on Amazon like years ago.
Didn't you use the money you got from like a chess competition to buy this or something?
I think so. I don't remember. It was actually ages ago. It's this thing, and like this, and it was like 30 quid on Amazon or something, and because I remember most of the stuff on Amazon was like for like artists and stuff, and so it's like really expensive because it had like fancy features. But like I just wanted to write stuff during talks, so I just went for like the cheapest option that seemed reasonable and like worked. And well, yeah, I ended up with this.
That's what you should do. I got one of those that was like $15. I think I offered to buy you one, and then you said no because you got money from a competition and used it to buy your thing or something.
Yeah, that does sound like something I would say, to be fair. Yeah. I should use it more. By that I mean I should give more talks here, because it is fun and interesting. But I just never do. But this winter is it's gonna go crazy.
Well, I mean, I guess you could just like, what if you and Ishan did the next talk together, like joint talk, even though you don't know anything about the code, just like learn. I don't know.
Just learn.
1 week.
Yeah, speedrun.
I think it's not hard to learn, actually. Python is almost just like natural language. You can just read it and it's fine.
Next time, do it in assembly, I think. Like,
no,
I think if you want...
assembly would be very efficient, but it would take me 10 years to write.
I mean, I do find that I can like sometimes read Python code and like understand roughly what's happening. But then when it comes to actually writing it, I have no idea where to start.
Yeah, it's easier to read than to write. But if you're just reading the stuff that we wrote, which is actually not very sophisticated code, it might be tractable. But yeah, I don't know. It depends on what we want to do next. Because if for the Meyer-Vittorius and Cech-de Rham stuff, I don't think. Well, that's not true. Okay, if we want to check that the Cech and de Rham cohomologies are the same, then I would want to implement the check in code and actually explicitly numerically verify. So that would actually involve some coding. But at the moment, I mean, we have to write out the complex and then see what the actual definition of the Cech differentials is going to be.
Yeah. Well, that should be okay.
CJ is typing. What is the question going to be? I forget who CJ even is, to be honest.
It's I don't even know what the like name is on the Discord. It's the Indian guy.
Oh, Pranat's friend, the other.
Yeah. No. Pranat.
It is Pranat. Oh, wait a second.
Yeah.
I thought it was his friend that they were the yellow submarine guy or something, but okay, I forgot.
No, it is.
Guys, it's me. It's Pranat.
Yeah. It's Pranat.
Okay, so I forgot that was your name on here because I was expecting William Buttlicker or something.
Yeah, and that's the ID that I use on my phone. Yeah.
What were you typing?
With my
A
PC.
serious question you were.
Yeah, I had a question, but I mean, I don't think it's a good one. It's just, since you had defined co-differential already, that check its ellipticity if it's an elliptic operator.
I couldn't understand the question. Sorry, you said we defined a co-differential, so did we check if it's what?
So can we define a Laplacian as d delta plus delta d?
Yeah.
Yeah, we did it in the paper. So we defined it. Yeah, it's and it has properties like Laplacian kills a form if and only if it's killed by both d and delta. So there's forms and all that stuff. Yeah.
And it's elliptic.
I don't know how to define elliptic in this case because it's not acting on functions. It's acting on like a list of matrices.
Yeah, exactly. So I mean, to prove, first we would have to define what an elliptic complex is. Even in this case, you guys would have to do that. Then check if within that premises what it even means.
Yeah, I guess, I mean, that part's kind of non-trivial, but I guess, let's see, can we guess what ellipticity would have to mean? Let's stare at the definition for 1 second. So if we were doing manifolds, you would say, okay, you have a differential operator on a manifold, which is a sum of derivatives. So in our case, this would be like a sum of tensors with the identity, right? Because derivative is tensor with identity for us. And then the definition is elliptic if and only if for every non-zero vector field C. So you need a vector field C. The sum of the coefficients of those derivatives contracted against the X's is non-zero. So first of all, we would need a notion of vector field C, which I guess in this case, let me think. I think the analog of vector field should be essentially entanglement forms, but with an upper index, right? Because we don't want numbers. Sorry, is that true? Actually, no, I don't know. Maybe this should just be a vector field of numbers because you could extract the coefficients of these things. Actually, yeah, okay. If you do it this way, maybe it's not so hard. You just strip off from the Laplacian, all of the numbers multiplying tensors with identity, and no, actually, I'm confused. I'm confused about how to do it because our Laplacian is delta d plus d delta, so it sends a k form to another k form. It doesn't tensor with the identity, so there's no derivatives acting really in that sense. The derivatives are all gone, which is kind of weird. So yeah, I don't know how to define it. I guess you would need a generalization of this because for us, there's no real derivative. There's just tensors with identities. So yeah, the short answer is I don't know. It's an interesting question though.
Well, why is it? Why? So what is the Laplacian elliptic in just like normally? Or
Yeah, I think so. Because normally, like the Laplace equation is the simplest example of an elliptic partial differential equation. So the Laplace is supposed to be elliptic, and then if you deform it a little bit, so instead of Laplacian, it's either like a heat equation, then it's parabolic, or if you deform it to a wave equation, then it's hyperbolic. So ordinarily, differential equations are either elliptic, parabolic, or hyperbolic, and the Laplacian is the simplest example of an elliptic operator. So I guess the question is this thing also elliptic? And there I don't know
I
how.
mean, it could be pseudo-elliptic as well. I mean, it could appear that it
Wait,
could
sorry,
be
can you say it again?
pseudo-elliptic.
I couldn't hear it.
Pseudo-elliptic. It could be pseudo-elliptic as well. That's what I'm saying.
Pseudo-elliptic, you say? Yeah.
Yeah, because it's not fully clear. It
Yeah, it's not even
even
clear how to define the
yeah
coefficients, right? Because the
yeah
derivatives are weird.
because
The derivatives.
I was reading about this stuff in this book by Charles Nash. Differential topology and quantum field theory by Charles Nash. He discussed index theorems and stuff. So of course we discussed
Yes.
this.
Yeah, this is kind of connected to, Tom had some idea to relate this to Morse theory. I mean, that's closely
Yeah,
connected to
yeah,
the
yeah.
properties of these operators.
That's a good idea. To even with no shade, makes sense. Would have.
I can show you what he said. I mean, he emailed me this 2 hours ago and said, this was after a string of like 3 other long emails where he sends all this stuff. And then he says, by the way, I realize there's an important direction. Wanted to use SUSY techniques like the Morse theory paper. And then he says, having the Hodge Star structure gives the entanglement complex the structure of a representation for the group of automorphisms from R01-1. So this is a superspace that has one spatial bosonic coordinate and one fermionic coordinate. So it's a superspace. And then you have a SUSY algebra generated by Q is d star, and Q star is I times d minus d star, and then a Laplacian. So this is what you do in supersymmetric quantum mechanics to get the Euler characteristic of a manifold that a particle is moving on, a supersymmetric particle. That Euler characteristic is just the Witten index of the supersymmetric quantum mechanics describing the motion of that particle. So Tom is suggesting here to play that whole same game, not with supersymmetric quantum mechanics, but with a version of the entanglement complex. So you do entanglement cohomology with like some supersymmetric target space under the hood, which then he talks about this partition function. It's related to the state index from his paper. So this is an interesting direction, and it's close to what you were just saying because yeah, like in the Nash book, it closely relates to Morse theory, right? This is the whole Witten story with SUSY and the Witten index and various indices like you study in Morse theory.
I still don't really know what the state index is.
Yeah, I always forget this. I mean, Tom, it's actually very weird because when we read this paper, I think we came away with the conclusion that the cohomology is the most interesting thing and the state index is like a side comment. And Tom, when we talked to him, he's like, the state index is the whole point of this paper and the cohomology only exists to define the state index. He's like completely backwards, which, where's the definition of it? Am I even in the right section? Where is it? The state index, yes. This is the Euler characteristic of some, but which chain? I think he has a later definition where he defines it in terms of the commutant. The search for an Euler characteristic. Yeah, the problem is this section is not very readable.
Mhm.
Findence. I just want the definition of the one he uses. And he has these box diagrams. Here we go. Here's an explicit state index. Okay, one option is the exponential of the von Neumann entropy, but that's probably bad. Because I remember it had a bunch of variables. Yeah, it had like an alpha.
Yeah.
Is it?
We define the state index as the function.
But he didn't tell us what this math script x is. It's
where that is that.
Okay.
What's D?
Yeah, now we have to. Yeah, now he has to tell you what D is. It's like only the things he knows. And he goes through this very laborious construction. There's just a formula for it somewhere, I thought. As indicated, okay. Yeah, he has formulas for its derivatives. Okay, this part I remember, because when you take various derivatives and set quantities equal to 1, it gives you simpler things like mutual informations, I guess. And it also gives you, somewhere it gives you the cohomologies, I think. Yeah, it gives you von Neumann entropies. It gives you Salas-Renyi entropies. But yeah, the actual definition of it is very difficult to decode because, yeah, I guess you're right. It's basically, the definition is this thing where you have to figure out what D is. Sum over Q's. And there's 2 commas there for some reason to make it even spicier. Q comma
R. I reckon that's a typo, no?
It is a typo. I'm making a joke.
Okay. Okay.
No, it's a very sophisticated mathematical double typo.
Okay.
Yeah, I don't even know where the D is. The script, the curly.
No. It's below. It's below that. He says X is blah 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 where D is, and then he defines it underneath, I think. Yeah.
It satisfies the multiplicative property. Does he construct it, or does he just say there's a unique thing that has these properties?
Oh, maybe he does. Maybe you're right. Maybe it is above somewhere, but
I don't think he actually defines it. I think he just says that there exists something with these properties.
Okay.
And I think that's why he was excited about the harmonic forms, because he kept telling me, oh, using your harmonic forms might let me write down a definition of the state index. And I was like, what do you mean definition? I thought you had a whole section on that in your paper. Like, yeah, I think he has no way of computing this thing, basically. It's just only certain derivatives evaluated at certain points.
Yeah. I also remember in section 9 there's some integrals for some reason, but I don't remember why they appear.
Yeah, that maybe in special cases.
Yeah, state indices.
Here, so for these states he can compute them. And here they're explicit sums of things. Okay.
Okay.
So only for particular states can you compute this, but I think not for a generic state.
Okay.
I guess you can ask.
But yeah, I still don't understand why. I mean, no. Okay, fine. If in special cases they are like, I don't know, interesting things, then I guess it makes sense why they would be interesting. But I still don't get like. Well, I guess even he doesn't really know exactly what they are. I guess nobody knows what they are.
Well, yeah, probably if he doesn't, then no one knows what they are. But I think the point is to categorify these things in the same sense that, like, you know, when you study knots, you study like knot invariants, and then you categorify them in some sense. So you lift certain knot invariants from just numbers, like the linking number, into a polynomial like the Jones polynomial, which is like our Poincare polynomial. But then you can lift it even more. So you can lift the Jones polynomial, which is a function of 1 variable, to a function of 2 or 3 variables, which are more refined. And with the property that if you take the 3 variable guy and set one of the variables to like 1, or maybe 2 of the variables to 1, then it reduces to the Jones polynomial. So he wants to do that same thing here where you put in more variables and make this thing more refined, because he was hoping that in cases where you can't tell the difference between 2 states based on their cohomologies, that the state index might distinguish between them. But I don't know if that's succeeded, and I don't remember if his code, state functor stable, did he even have places where you can compute the state index in this thing? Cats. Oh yeah, entropy's in the state index. Okay. All right, so I guess he can compute state indices of something, at least certain states. I guess he has some code to brute force it or whatever. Well, yeah, that could be interesting to look at as well, but I don't understand it at all at this point. I mean, as you recall, we read it, and my attitude was like, I don't understand this. Let's just work with the cohomologies because I think I understand that a little bit.
Yeah. Who knows? I don't know. I'm fine with sticking to the cohomologies.
Yeah, I think you seem to like this better because you like homological algebra, right?
Yeah. I'm in my comfort zone right now.
Yes. So eventually you have to journey out and do other things outside your comfort zone. But for now, yeah, it's good to get started with research now that you have your first paper out. So you're a freshly minted researcher. You can do some stuff in your comfort zone for a while.
Yeah, exactly. Yeah.
The comments in the chat are Incy saying, Lumfao, bro is really thinking on this. OMG, the pink comment boxes using pastel colors is actually so brilliant. I guess he likes Tom's paper formatting.
I mean, the formatting is nice, but it's just long and dense. The actual words inside the formatting.
I think ours is better. Ours is still dense and the notation is it's not perfect. It's a little hard to read sometimes, but I still think it's better than his. It's like more direct and it explains things faster, I think.
Yeah, I mean, I'm very biased because, well, I could say like, oh, I understand our paper just from reading it, but that's also because I was thinking about it for
2 years.
Like a year. Yeah, 2 years. So I guess I can't really be very objective.
Well, I mean, other people Arcat read it in like a month and understands it, I think, basically. So that's probably a good sign.
Yeah. Okay. Yeah. Fair enough. But maybe he would have understood it better if we put pink boxes.
Maybe. I mean, I think I'm going to have to veto that suggestion for version 2, that I don't want any pink in the paper, but maybe if you solo author a paper, you can put pink in.
Yeah.
Oh, gosh. All right. Well, I will stop the recording now since I guess that's